Here we go, review of the urinary system, part 3. On this one, let's take a look at the juxtaglomerular apparatus and how it's involved in trying to regulate the activity of a single nephron. So here is our grossly twisted out of shape nephron. Here's the interlobular artery or cortical radiate artery that's found inside the cortex. Here's the afferent arteriole delivering blood to the glomerulus inside the capsule. Here's the efferent arteriole taking the blood out to the peritubular capillaries. Here is a twisted view of the nephron, in which here's the capsule, here's the tubules and such leading to the distal convoluted tubule. Or if we had to show it somehow, kind of sort of like this right here. Afferent arteriole, glomerulus, efferent arteriole, peritubular capillaries, glomerular capsule, proximal convoluted tubule, loop of Henle, and distal convoluted tubule. All this set up just to show where the juxtaglomerular apparatus is located, right here, where the distal convoluted tubule and the afferent arteriole bump into each other. That's AA for afferent arteriole. Now, in this structure right here, the cells in the wall of the arteriole increase in size. The cells in the wall of the distal convoluted tubule increase in size. On the arterial side, they're called granular cells. On the distal convoluted tubule side, they're called macula densa. On the arterial side, you have mechanoreceptors measuring or recognizing the blood pressure inside, and they're capable of producing renin, which can indirectly cause an increase in blood pressure if it becomes necessary. On this side right here, you have the macula densa cells, and these things have chemoreceptors that are judging the solute content of the filtrate. In essence, this is a regulation station where it's looking at what's coming in to see if there's adequate pressure, and it's looking at the product from the last blood that was processed through here. And it, in essence, is going to decide how fast or slow the blood will be moving into the glomerulus, what the glomerular filtration rate should be, and what happens down through the tubes right here. The analogy to be made right here, it's got the same kind of an attitude as a precapillary sphincter, in which one structure is taking care of one little neighborhood of cells. Well, each nephron has a juxtaglomerular apparatus, and it, in essence, is regulating the blood flow for its nephron. Again, please remember there's approximately 1 million nephrons per kidney. So again, each one is independently being controlled like this. Here's the big story. If, for some reason, the blood pressure going into the glomerulus goes down, what will happen is the glomerular filtration rate will drop. Since there's less pressure inside the glomerulus, there'll be less pushing force to create filtrate. So if the blood pressure goes down, the glomerular filtration rate goes down. If that happens, then the volume of filtrate being produced will obviously go down. As there is less material moving through the tube, the velocity of the filtrate goes down also. And now here's our dilemma. As you slow down the filtrate going through the tube, the cells that line the tube, the simple cuboidal cells of, say, the proximal convoluted tubule, now have more time to gather materials from the filtrate. And in essence, what they do is they gather too much materials. At the proper glomerular filtration rate, which is approximately 180 liters per day, 125 milliliters per minute, that's just the right amount of time to get just the proper amount of materials out of the filtrate, return it to the blood, thereby ensuring that you have 100% of the normal levels of materials that you want, and everything else can't be caught, everything else will fly by. But in this situation right here, the material's moving so slowly, not only do you catch what you need to catch, but you have time to catch a little extra also. So you inadvertently reabsorb too much material. Therefore, there's less material left inside the filtrate, and the concentration of solutes inside the filtrate goes down. If this is the case, the juxtaglomerular apparatus has a reaction to that. The cells of the distal convoluted tubule recognize that the solute concentration of the filtrate is going down, and it responds by decreasing vasoconstriction going to the afferent arteriole. Now, if the afferent arteriole has less vasoconstriction, that means that the lumen of the afferent arteriole becomes wider. If it becomes wider, there's an increase in blood flow going towards the glomerulus. If you have more blood entering the glomerulus, things get crowded in there, and that means that the blood pressure inside the glomerulus will go up. If the blood pressure goes up inside the glomerular filtration rate will go up. You'll push more materials out of the blood and into the filtrate. The volume of filtrate will go up. And as you continue to push this material into this narrow hallway of sorts, the velocity will go up. But as the material starts moving faster and faster, it starts flying by those microvilli and their integral proteins that are supposed to be grabbing 100% of the normal amounts of nutrients and such. And so therefore, the tubular reabsorption goes down. The things are moving too fast. We mentioned it's like working next to a conveyor belt in a factory of some sort, and they speed up the belt too fast. You can't do your job. And my terrible analogy, this is like a teacher talking too fast. You can't write it down. It's all going by too fast. Well, if you don't pick it out of the filtrate, then that means that it stays inside the filtrate, and the concentration of solutes inside the filtrate goes up. The chemoreceptors of the juxtaglomerular apparatus recognize this, and they will respond by causing increased vasoconstriction. Increased vasoconstriction means that the lumen of the afferent arteriole will become more narrow. If it becomes more narrow, it acts like a gate, and it restricts the flow of blood through there. So there will be decreased blood flow into that region. The blood, in essence, will be diverted to other structures along the interlobular artery. If the blood flow goes down, then the pressure inside the glomerulus will go down. The glomerular filtration rate will go down, the volume of filtrate produced goes down, velocity goes down, tubular reabsorption goes up. You gave the cells too much time, they'll take what they need plus more. There's a decrease in solutes inside the filtrate. The juxtaglomerular apparatus has a reaction. It causes decreased vasoconstriction. You increase the blood flow heading towards the glomerulus, which causes crowding inside the glomerulus, and you can see the story goes back and forth. So it's an example of a homeostatic mechanism in the sense that there's an ebb and a flow of the blood moving through this area. Now, all of this is based on the idea that there is at least a minimum amount of pressure inside the interlobular artery. For example, it needs to be about at least 45 units of pressure according to mean arterial pressure. So the nephron is very much concerned that there needs to be blood pressure, which is why the juxtaglomerular apparatus has the ability to make renin, and by doing so, it can actually increase the blood pressure. Once again, the juxtaglomerular apparatus, like a precapillary sphincter, is taking care of its neighborhood.